Welcome back to linear algebra. In this video, we're going to be looking at the idea of a subspace. The name subspace kind of is as obvious as it seems. You're familiar with the idea of a subset of a set. A subspace of a vector space is going to be a vector space contained entirely within that vector space. But the nice thing about a subspace is that it has to share the operations with the original vector space. And the reason that's so nice is that showing that something is a vector space shows you a lot of properties of that vector space. And a lot of properties of the operations. So if we are inheriting operations from a set we already know is a vector space, we gain most of the properties of a vector space immediately without needing to go through them. So let me get my head out of the way. Let's formalize that definition and see what we can do with it. So if we have two vector spaces V and W, we say that W is a subspace of vector space V if and only if V and W use the same definition for vector addition and scalar multiplication, and W is a subset of V. In order to use this, we want to consider a vector space V, and we want a subset of V we'll call W. And we do have to insist that it is non-empty. Remember from the last video that the empty set is not a vector space. So having a non-empty set is important. Then just with that, we have a non-empty subset of a vector space. And we're going to say that that non-empty subset is a subspace if and only if it is closed under both vector addition and scalar multiplication. The proof of this theorem is actually not that bad. Notice that this is an if and only if statement, so we have to prove both directions, although the first direction is pretty easy. If W is a subspace, well, the definition of a subspace says that W must be a vector space. And vector spaces are, of course, closed. That's the properties of vector spaces, so we don't have to show that again. But we do have to look in the other direction. So we will assume that W is a or V is a vector space. We will assume that W is a subset of V, and we will assume that W is closed. So that is to say that U plus V is in W and K times U is in W for any U and V in W. And we want to show that W is a vector space. Showing something that is a vector space, we have those properties. I numbered them using 6 properties. The textbook numbered them using 10 properties. W is closed. That's our assumption. The commutative and associative properties we automatically inherit. V is a vector space. Because V is a vector space, the vector addition must be commutative and it must be associative. That has no bearing on which vectors are or are not available, so we don't have to do anything else. The properties of the zero vector, on the other hand, we do have to worry about. So we have to get a little bit creative. And here I'm going to turn to not the properties of a vector space, or not the definition of a vector space, but some of the derived properties that we proved about vector spaces. Namely, 0 times V is 0, and -1 times V is the opposite of V. Right? That is true of any vectors in any vector space. So since W is closed, we pick some vector in W, and 0 times V is 0, must be in W, And -1 times v is the opposite of v, must be in W. So the 0 vector must be in W, and the opposite of every vector in W must also be in W. If that were not the case, then W would not actually be closed. And the 0 vector is going to have the properties of the 0 vector because we inherit it from V. The opposite is going to have the properties of the opposite because we inherit it from V. And then we can go through the rest of the properties. The distributive property, the associative property for multiplication, and the property of multiplying times 1. Once again, those are all things that we're going to inherit from the vector space V. So right, because V is a vector space and the scalar multiplication is defined the same, K times U plus V must be KU plus KV. Whether those vectors came out of W or not, W is a subset of V, so those vectors still came out of V. And those are the properties we need. So just that one trick of showing that the 0 vector and the opposite are in W saved us an awful lot of headache. Right. Now that we have that, let's play around with it a little bit. Consider W the set of Euclidean vectors x, y, z, so that z is equal to x plus 2y. And I claim that W is a subspace of R3. Well, based on our theorem, we need to show 3 things. First, we need to show W is non-empty. We can pick any vector that we can figure out. The easiest one it looks like it's going to deal with is if x is 0 and y is 0, well, z is defined. 0 plus 2 times 0 is 0. So the 0 vector is in W. That's an interesting property of a vector space that normally we would have to show anyway. For our theorem, we don't specifically need the 0 vector to be the vector in W, but we do need some vector. We need something in there to show that we're not dealing with an empty set. Next, we have to show that we are closed under addition. Well, with this definition of vector space W, we can pick any values we want for the first coordinate and the second coordinate, and then the third coordinate is automatically given to us. So pick two vectors, right? Pick x equals a, y equals b. The third coordinate must be a plus 2b. That's the definition of w. Likewise, pick any x, pick any y. The third coordinate must be x plus 2y. Well, using the properties of vector addition for the Euclidean vectors, we get a plus x, we get b plus y, we get a plus 2b plus x plus 2y. And if we take the x component here, a plus x, plus 2 times the y component, b plus y, we get a plus x plus 2b plus 2y, and we can use the commutative property and the associative property for adding real numbers to rearrange this as a plus 2b plus x plus 2y, which is exactly what that third coordinate looks like. So by the definition of W, this thing is in W, which means that we are closed under addition. And then a similar idea to prove closure under scalar multiplication. We're going to take a scalar k. We're going to multiply it times an arbitrary vector out of W, x, y, x plus 2y. And the rules for multiplying, or for scalar multiplication in the Euclidean vector space, tell us that this is going to end up with kx, ky, and k, x plus 2y. But we can test the rule for our subspace here. We need the x component, which is kx, plus 2 times the y component, ky. And notice that there's a common factor of 2 we can take out here, leaving behind x plus 2y, which is exactly what we have in the third component. So this is also an element in W. By the theorem on subspaces, we have a subspace of our vector space. Sometimes this example makes it feel like subspaces are just incredibly easy to come by. So I'd like to do one more example to show you how much on a hair's breadth this definition of subspace comes in. Consider W, the set of all x, y, z, such that z is x plus 2y plus 1. Almost the exact same subset we were looking at before. But with just that slight change, all of a sudden, we no longer have a vector space. Well, to show something is a subspace, you want to show that it is non-empty, that it's closed under vector addition, and that it's closed under scalar multiplication. To show that this is not a subspace, we want to show that at least one of those properties is not true. This is still a non-empty set, so that doesn't help. We could show either that this is not closed under vector addition or that it's not closed under scalar multiplication. Both of those are true. Scalar multiplication turns out to be a little bit easier. So knowing what I know already about this set, I'm going to choose that one to look at. So take a scalar, k, times an arbitrary vector out of W, which in this case would have the form x, y, x plus 2y plus 1. By the definition of scalar multiplication in the Euclidean vector space, this is going to be kx, ky, k times x plus 2y plus 1. And if we look at our equation, we want z to equal x, which is kx, plus 2 times our y, which is ky. And we could factor out the k, and we would get, k times x plus 2y. But that's not what we have down here. We have k times x plus 2y plus 1. So k times x plus 2y, I think you'll agree with me, is not the same, is never the same as k times x plus 2y plus 1. So W is not closed under scalar multiplication. And because W is not closed under scalar multiplication, it does not satisfy those properties to be a subspace. And in fact, it doesn't satisfy the properties to be a vector space in any way, shape, or form. So it could be that there's a different set of rules that will make this a vector space, but the Euclidean definition of vector addition and scalar multiplication does not work. Now let's start to get somewhere interesting. Let's let T from Rn to Rm be a linear transformation. Remember from an earlier lesson that a linear transformation on Euclidean vector spaces can always be written as matrix multiplication. So T of x we can write as matrix A times x. The kernel of T, which we denote as KER of T, is the set of all x in Rn such that A times x is equal to 0. The kernel of T, the kernel of this transformation, is the set of all solutions to the homogeneous system of linear equations. And working backwards, given any linear transformation, we can always establish a kernel. Every linear transformation has a kernel because at the very least, the zero vector always satisfies the homogeneous system. So there's definitely always something there. Not only that, whenever you have any homogeneous system of equations, you can rewrite that using a matrix. And if you have a matrix, you can multiply it times a vector and call that a linear transformation. So the vocabulary here can get a little bit messy. Technically speaking, this should be the kernel of the linear transformation T. Sometimes you will see it called the kernel of matrix A, and every now and then you'll see things go a little bit haywire there as well. We can also call this the solution set of A, or in fact, the solution space, right? The kernel of T is the solution set of the equation AX equals 0. And given when we are talking about this, it shouldn't be too much of a surprise to you. That my theorem is that the kernel of the transformation is a subspace of Rn. The kernel is a vector space. The solution set of a homogeneous system of equations is a vector space. All right, step one, to show that something is a subspace, you have to show that there's an element in there, show that the set is not empty. It doesn't have to be the zero vector, but the zero vector is very often the easy one. In this case, if you take any matrix and you multiply by the zero vector, you will get the zero vector back out. And that's what the equation tells us is supposed to happen. So the zero vector satisfies the homogeneous system, which means that the zero vector is in the kernel. Let's now take a couple of vectors, u and v, out of the kernel of T, and consider A times the sum u plus v. We know that matrix multiplication distributes, and vectors are really just matrices. So this is going to distribute. You'll get A times u plus A times v. And from here, the definition of being in the kernel, A times a vector in the kernel has to give us the zero vector. And if you add the zero vector to itself, you get out the zero vector. And since A times this sum is the zero vector, that means that u plus v also satisfies this system of equations, satisfies the homogeneous system. So u plus v is also in the kernel of T. Right? Likewise, let's take a look at, I can write it better than that. My writing is horrible, but I can do better than that. consider the matrix A times K times U. Once again, using properties of matrices. So remember, even though U is a vector is just a column matrix. And if you're multiplying a scalar times a matrix, you can multiply that scalar times matrix A times the column matrix vector U, or times the product, and you get the same thing. So this is K times AU. And since U is in the kernel of the transformation, that means that A times U is the zero vector. And I know that if I multiply any scalar times the zero vector, I get back out the zero vector. So K times U is also in the kernel of T. There we have it. Kernel of T is non-empty, closed under addition, closed under multiplication. That's what it takes for something to be a vector space. This particular vector space, for some matrix A, the kernel of that matrix turns out to be a very important vector space. It's going to be very valuable to us in several of the things that we're looking at. So don't be surprised when this comes up frequently as a way to build out a vector space. There are two common ways of building a vector space as a vector subspace. This is the first one. In the next video, we'll take a look at the other one. I'll wrap up here, take a look at some of the practice problems on subspaces, and I'll see you in the next video.